immediate action reward. So now, as I told you, when you have this reward transition model, so if you know the distribution, the reward that you are going to collect and the next state, you're able to pretty much compute anything that you want. Okay? So, for instance, say that I do know that model, that particular distribution, and what I'm looking for is to see that if I am in one particular state S, and I do one particular action, immediate reward that I'm going to collect. Okay? That is quite easy, right? What I'm going to say, okay, the next reward that I get, given that I am in this particular state and this particular action, I do this particular action, then it's going to be this expectation, right? And can I compute this expectation with the environment? Can I know that distribution? Yes, I can do it, right? So I can write it down in this form. So I would say any reward, say RL, is happening with the probability of RL given as NA. So I'm going to put it inside the summation, and I compute the average immediate reward that I'm collecting. Okay? And of course, as I told you before, if you don't see this distribution immediately, since you have this other distribution, you can simply first marginalize, and then after marginalizing, you can do the averaging. Okay? Everybody's cool, right? Questions? So immediate reward, you can compute it, right? Now, the question is, yeah, that is the rewarding transition model. Oops. Now, this guy that we computed right now, this one, this average here, is going to tell you what is the immediate reward, right? But at the end of the day, what you want to have the rewards toward the end, the average return that you are going to collect, right? And if you want to do that, then it's going to be a bit. Now, let me first give you a name, okay? So this guy, this is what we call it the immediate reward. And this immediate reward is of this form. So whenever from now on I'm going to tell you average immediate reward, I'm simply talking about the average next reward that you're going to get given that transition that you have inside the system, right? Now, next thing, can we somehow relate this guy to our policy? Or in other words, are we able to compute the value function? So yes, we can actually do this guy by averaging it over the policy, right? For instance, say I have this particular policy pi, okay? And now I want to know what is the average next reward that I'm going to collect, given that I am playing with this policy pi, right? I want to find that out. How can I do this? Well, I could say that if I am playing with S and some particular A, I can compute it exactly like the previous slide, right? And now, if I just know my policy, then I can get the chance of every single action given my policy, and then I average over that one, right? So that is going to be the average immediate reward that I'm going to get if I play with policy pi, right? So I can say that what if I do as the next action AM, so this particular action, well, this one is easy, right? This one is exactly this guy, right? We can compute it given the transition and rewarding system that we have. If we have that guy, so I have this guy, I just multiply it to the policy, so the chance of doing AM, and then I average it over all of them, right? This is going to give me the average immediate reward that I'm going to collect at a particular state S if I play with policy pi, right? So I hope that you feel comfortable with these notations. I do know that it is too much of like indices and too much of summations, but you don't really need to focus on details, just get the big picture, right? So the environment is actually explaining what's going to happen next, and then you can just use that one statistically to just compute the average reward. Yeah. It's just the first term, right? It's not the value function. This is the immediate reward. We have not yet computed that one. We're going to compute that one as well. Yeah. Questions? So, yeah. Let me know if this question is unimportant. Of course. Is this expected reward what we get upon entering the state or upon making an action from within? Upon, you can assume upon making an action. Okay. Yeah. Yeah. Let me think. No, I would say upon entering the next state. Yes, because you don't really need to think too much about that, but just since you asked. So you're talking about reward and state, next state, given the current state and the action that you do, right? And then it depends how you interpret it, but if you write down the chain rule, the more natural one is that you say that the probability of the next state, given the current state and the action that you're doing, right, times the probability of the reward that you're collecting, right, given the next state, current state, and the action, right? This is the chain rule, correct? And then you could say that next state is somehow, you do first the action, and then you're in one particular state, then you're going to get to the next state, right? Once you got to that next state, then given that what was your previous state and the action, you're going to get the reward, right? You can think about it like this. But mathematically, you can also write it down as R here, S bar here, R, right? And then in that case, you get the reward upon doing the action, and then you move to this state, right? It's just how you think about it. It doesn't impact the formulation. Questions? No question? Okay, cool. So, yeah, that guy here, so as I said, this is the immediate reward that you're going to get when you play with your policy and you're in a state S. And you can simply compute it. I do know this is too much of summations here, but at the end of the day, this is possible for you to compute because you have this P, this distribution. You have pi. This is your particular policy that you are playing with. And then you can simply compute these marginalizations. Okay? Cool. So let's grid world and see, for example, how does the immediate reward look like here. Say, for instance, that, I am in one particular state. This state is state 1. And now the actions that I can do, all of the 4 actions that you can think of. So if I do action 0, I would definitely go to this cell. If I do any action 0, or if I go left or down, I'm going to end up taking one step, which is going to be -1. If I do action 2 or 3, like right or up, I'm going to just hit the wall, right? Then I'm going to collect each time reward -half, right? And then I could say that the average reward that I'm going to collect is going to be exactly these ones because the transition is happening deterministically, right? There's no randomness here, right? And now you can actually, or for instance, if you're in the terminal state, you do any action, you always end up having 0. This is something obvious we said before. But you can also compute the average immediate reward when you are here, regardless of your action, given your policy. So you forget about the particular action. You would simply say I'm playing with one particular policy, then what is the average reward, right, that I'm going to collect immediately? For instance, say I am playing with I am in one state. I simply choose one direction, and then I move. Okay? If I do that, this particular example that we had here, this one, when I am in this particular cell, if I play with that random policy, what's going to be the average immediate reward that I'm going to get? What is it? Please? It's going to be minus 0.75, right? So you're going to be the average of these two, because 2 times you're going to get -1, 2 times you're going to get -half. The average of them is going to be minus 0.75. So this is basically the one we showed in the previous slide, the immediate reward that you're going to get in one particular state given all the actions, multiply with your policy, and then you sum it up over all possible actions, right? Everybody's cool? You see it? Cool, great. Now, if you do a deterministic policy, for instance, you are here at this particular point, you always go left. This is somehow the optimal policy, right? So if you do that, then your pi in this case is going to be 0 everywhere except the action of going left, right? And then the reward that you are going to collect, the average immediate reward, is going to be -1, right? Everybody's cool? Questions? No question? And you can go ahead and compute for this particular policy that we have here, the other guys, the other average value at other cells, and you're going to see all. You're just going to the neighboring cell. Yes? No, we have 2 minus 1s to minus 7. Because when you are here, if you go left or down, both of them, your immediate action, you're going to collect just -1. Yes. If you go here, you just get -1, and after that it's always 0, right? If you get here, then you're going to be -1, for example, then -2, -3, then 0, right? Okay. Questions? No question? Okay. Now, one thing here, everybody pays attention to this one. I put this numbers here, on purpose, because of one thing. Like this policy here that you have, the policy of moving in this direction, this is a deterministic one. This is obviously the optimal policy, right? Or a optimal policy. It's not this is not the only one, but it's one of the optimal policies, right? Because at every cell you're taking the shortest path, right? But now, at the particular one that you are, what is the average reward that you're collecting? -1, right? What about this policy here? What is the average immediate reward that you're collecting? This is -0.75, right? This is more than the other one, right? But the key point is that this is only for state 1, right? It's not towards the end. It's just for the immediate action that you do, right? So if you are very greedy, you're going to say that this guy is giving me immediately more reward, right? Why should I do the other policy? Why should I just move towards the end, right? But the key point is that when you do this, in those occasions where you just hit the wall, you keep on hitting the wall, right? You are collecting more negative rewards, right? So this key point that I wanted to mention here is that when you are looking at one policy, one particular policy pi, this is not important for you that what's going to happen immediately next, right? And this was the main reason that we defined and also the value function to be the expectation of that future return, right? Because if you think only about the immediate reward that you are getting, sometimes policies are going to give you better immediate reward, right? When you are playing chess, sometimes like you take your, I don't know, bishop and you just hit the queen, right? Yeah, wow, I got like a huge mark, right? But you're over probably after a few moves, right? So this is the key point that you should pay attention to. So not immediate reward is not the one which you are looking for, right? And this is why we define the whole value function. Everybody's cool? Question? Question. To the serious job, and that is to just compute the value function. It means that if I want to play with one particular policy, what's going to be the expectation of the future return that I'm going to collect towards the very end, right? And since I do know the environment, then I can eventually describe or evaluate this value function. Like, theoretically, I can do it, right? But it might be a bit complicated in terms of computation, like I need to do lots of computations. Now, what I'm going to do first, I'm going to call it naive approach. I want to just do it naive approach, like the one which we started to think of in chapter 1. And once we just do it, we see that we can do it, but it seems like something very exhausting. And then this is going to motivate you why we need to just use a recursive property of the return, and then we end up with a Bellman equation. Okay? So let's start with this naive approach. What I want to do, I want to just calculate the value function. So I assume that I'm playing with policy pi. I am in one particular state S. And then this is the definition of the value, right? The average future return that I'm going to collect, given that I am in that state and I'm playing with the policy pi, right? Now, I can open it up. I've done this last time. And then I can just write it in form, so I just expand the expectation, right? So it's going to be the expectation of the immediate reward, is the expectation of the second immediate reward, and so on towards the very end, right? Now, the phi is OK. Yeah. So that was the immediate reward you get at the particular state. I'm going to replace it. The things remain are these guys, right? So I need to compute those ones. And now, well, let's start with the first one, right? Let's see, for example, what's going to happen to this first term. Since I do know the transition and rewarding, I can explain what's going to be the second next reward, or I can explain the distribution of the second next reward given my current state and action. I can describe it. And when I describe it, I can average over it to find out what is the expected second reward, right? So let's do it together. Let me know again, this is a bit confusing, but I used lots of colors to just make it clear for you. So what I want to do, this expectation is not the one which I have here. This is not that one. This is a new expectation. In this expectation, I assume that I am currently in a state S. The green guy is my current state. Then after first action that I do, so I do the action AT, this red variable here, AM. I do one action AT, and then I'm going to change to another state, right? So assume that the next state is going to be as the the yellow state, okay? And say that after getting into this state, I do the action, blue action AT plus 1, okay? So I was in one green state. I did a red action. I went to a yellow state. I do a blue action, okay? Now, I want to know what is the expectation of my second next reward, RT plus 1. Now, if you're looking at this one, if I want to just write this guy down, okay, what should I do? I would say, okay, I want to know the expectation of the second reward, the expectation of this guy, given all of the next pairs. So the pair at time t, the pair at time t plus 1, right? So and I can write it down in this form. But one question, given that we have a Markov decision process, if I do know the state in action at time t plus 1, do I need to care about state in action at time t? No. Yeah? I can throw this guy, right? Everybody's cool, right? So I can just throw away the state at time t and the action at time t. So the green and red guys are going to vanish. And the reason is because since I do know what is the state at time t plus 1 and the action at time t plus 1, I don't care about the previous ones, right? If I didn't know them, then I needed that. But since I do know them, I really don't need the previous state in action, right? So this is going to be the next expectation. But here what you see is the expectation given not only the current state, the second next state, and not only the current action, but also the next action, right? So that is OK. But now the question here is that what if I wanted to just compute this guy, right? I want to take the expectation with respect to only s, right? Sorry, given only s. And if I want to do that, what should I do to this expectation in order to get rid of all terms except the green s? Yes? Not a bunch of summation. I need to multiply with their distribution, then I do the summation, right? So important, pay attention to this one. Just look at it here. Say I have expectation of x given y and z, okay, for instance. And I want to get from this guy to the expectation of x given y. What should I do here? Chain rule, you can do it. But I don't want to open up the chain rule. I just want to do it intuitively. Let's say z could be a bunch of cases, right? So I'm going to say that what is, for example, z? Say zi, right? Or anything, right? Then I need to know what is the probability of this zi if y is at a particular value y. And I'm talking about y here. Just I need to know what is the probability of zi given that particular y, right? I'm going to say that when y is y and z is zi, I'm going to have this expectation, right? This is going to happen with this probability, right? Clear? Like when y is y, what is the chance of z being zi, right? So you multiply it. And you go for the next z and next z and next z, and then you average over all of them, right? So you're going to average over all of them, and then you are going to get to your average without z, right? So if z is at this side, you first need to multiply with the corresponding probability, and then you do the averaging, right? Everybody's clear, right? Okay, cool. Questions? No question? Sure? Okay. So now, if I want to do the same thing here, so I want to get rid of everybody here, all the other colors, right? So I'm going to put the probability of all the other colors given s, right? I have the feeling it's not clear. If it's not clear, just tell me. It's not clear? Okay. So what is the problem with this guy? Okay, let's do it another way. Say I have probability of x given y. When you have, expectation of x given y. When you have expectation of x given y, definitely you're going to put something here, right? So y equal by something, right? For instance, you would say y equals by, I don't know, say y is a binary case. So it's going to be 0 or 1. You would say if y is 0, then the expectation of x is something, right? If y is 1, then the expectation of x is going to be something else, right? Now, if you want to know only the expectation of x, what you're going to do then? Exactly. So you would say that once y is 0, and once I compute the expectation of x when y is 1, right? And then I need to add them up, but I don't add them up just simply, right? I'm going to say y is 0. What is the chance of y being 0, right? I multiply it to that, right? Plus the expectation of x when y is 1 times the probability of y being 1, right? Cool? Now, if you do that, then this is going to be the expectation of x, correct? Now, what if now I have another extra variable here. So it's not only y equal by 0, but I have, for example, z first equal by some other z. So say z equals by 2. And y equal by 0. Okay? And again, here I have z equal by 2. And then I put y equal by 1. Okay? Now, if I want to compute the expectation of x, given that z equals by 2, what should I do? I would say, OK, expectation of x, when z equals by 2, that one I have it already, right? And first case, y equal by 0, right? Again, expectation of x, given that z equals by 2, and y equals by 1, right? The other case. But when I want to multiply it with one distribution, what should be that distribution? Is it simply distribution of y equals by 0? Given that z equals to 2, right? So I would say, given that z equals by 2, what is the chance of y being 0, right? Everybody's clear now? So I'm going to put here, given that z equals by 2, again here, given that z equals by 2, right? I'm going to do that. Now it's clear? Yeah. So if it's clear, then you would see this one here. I want to compute. I know this is too much of notation, but you just look at the expectation. You want to compute the expectation of this RT plus 2. Given that you have S, your current state is the particular state S. So you're going to keep this state, and then you're going to average parameters, right? Does that make sense? So all of these other colors are essentially y for us, and that green S is essentially z. And then you sum up over all possible cases for these parameters, right? You see it? Yes? Yes? Clear? Or? Because I have the feeling I lost my time anyway. So just OK. So now, so basically what I want, I mean, this guy, right? Because the rewarding transition model that we have is going to give us explicitly what this distribution is, right? That one we can compute. After the summation, we have no problem with computing that. Okay? The problem that we have is that what is this probability distribution, right? So what is this guy? This is the probability this is the probability of your current action being AM, your next state being SN, your next action being AJ, given that your current state is S. Now, how can I open this up? So let's just write down the chain rule. I write down the first term. You tell me the other things. So the first term that I'm going to do, I'm going to write it down P of my current action AM given the current state, right? Now, what is the next term? Exactly. P of the next state given the current state and the action, right? What's going to be the next term? P of the next action given the current state, the current action, the next state, right? This is going to be the next one, right? Everybody's cool? Now, do I have this stuff? I have all of them. How? What is the first one? What is the probability of your current action given the current state? It's the policy, right? So this guy is right? What is given by our transition model? environment itself. I mean, the Markov process is describing it, right? What is the probability of the next action given your current state, current action? Right? So this is going to be the policy of the policy at the particular action given your next state, right? Now, you can compute this. You can put this here, and then this one also is computable, so you can compute this guy, right? And I don't expect you to just see it immediately. The whole point here is that you see that every single component inside this expectation is available. Right? Questions? I have a question. Do I see you on Tuesday here? Because you look like Superman. I mean, if you don't follow the details, it's okay. We're not going. This is why I called it naive approach. We're going to do Bellman later, right? But hopefully you are motivated that this is not a good approach, right? Okay, cool. So now. So what you can see here is that eventually this second expectation that you're computing is a sort of, super nested summation, but you can compute it, right? For t plus 3, right? If you want to do t plus 3, then again, okay, I condition it to the current state, current action, next state, next action, second next state, right? And second next action. And then you start doing the same thing as I did here, right? The expectation is possible to be written, and then that probability distribution you open by chain rule, and it's going to be a bunch of policy values multiplied with the Markov chain, the Markov process values computed at the particular actions and states, right? So you can always do this for any t towards the end, and this is the way that you can eventually think of computing the expected future return, right? But the key point here is that if you keep doing this, this is going to be a nightmare, right? So we did it just for second next time. You saw that this is a quite messy expectation. You can think if you want to do it for a general, say, t, then it's going to be a kind of non-tractable summation, right? And this is why this is not a very good approach. This is why I'm calling it naive approach. Okay? Okay, so before I finish with this naive approach, let's try to just look at this dummy grid world, and let's try to see what we saw there with like too much complication here, which is quite simple to follow. Okay, so I want to just compute the value of my policy pi1, and the policy pi1 is the one which I'm showing here. Okay? At every cell, I'm just moving in the direction that is indicating. And if I want to compute the value of the policy, since Markov chain is known to me, I can simply explain it. What is the average immediate reward that I'm going to get with this policy? I'm going to always move left, right? And then I'm going to always collect -1, right? So this guy is going to be always -1. Once I do -1, anything else is going to be 0 because I'm going to end up with a terminal state, right? So those massive summation that I showed you, all of them end up being 0 in this particular environment, right? Because all of those transitions and P of R, given that, all of them are going to be 0, okay? And because of that, you end up with your value being your immediate reward, which is -1, right? And do the same thing for every other cell. So you can, for example, go for 0. This is a terminal cell, so you don't need to calculate anything. The value is 0. For 2 and 3, you can do the same, right? You just follow the policy, you can do it. Okay? And all What about this policy? Well, eventually, this is the same policy. You can do the same thing, and then you're going to end up with the same values. Here, it's going to be -1, -1, and then -2, right? And one key point that you see here again is that policy 1 and policy 2, both of them are showing the same value, right? So here we had the same value, -1, 0, -1, -1, -2, and here we have, and both of them are optimal policies. But if you think about this policy, then eventually this one is more interesting, because if you just write it down for this particular cell, the cell down right, then you're not actually going to do it. Oh, no, not this one. Sorry, for this top right one. If you write it down for this one, this is going to take longer, right? Because the first time you're going to come here, then the Markov process is going to tell you what's going to happen, and then you again come here, and then you end up, right? And here, 4, right? And then this guy is not an optimal policy, right? So obviously, both of optimal policy, and they are better than this one, because in one particular cell 1, they are doing much better. Questions? No question? OK, so if you got no question, just to wrap it up, if you do know the environment, if you do know the MDP, which is describing your environment, you're always capable of describing what's going to be the next state and next reward, right? And because of that, you can always calculate the expected reward at any time in the future, right? It might be super messy, but you can do it, right? This is possible. And because of that, you're eventually able to describe the value of every single state that you have, right? But the only key issue here that you might see is, well, if we are dealing with a practical environment, then this kind of messy calculation that we have done here is not going to work, right? How can I say that? OK, say that I computed the immediate reward and I computed the second immediate reward. How can I compute a general, I don't know, L next reward? How can I compute the expectation of that one? And if you want to do that, if you want to stick to this naive approach, the only way that you can do it is that you just compute it by hand, and then you look at the rewards that you are getting, and you see whether you see a kind of pattern between them, so that you can sum them up, given that pattern, right? But that is probably not a feasible approach in most environments. So the better approach that you can do is to use what we call it Bellman equation. And what is Bellman equation? It simply comes from the fact that the reward that you are collecting in future is showing a sort of recursive behavior. Yeah? So this is the Bellman equation. What does it say? It says that, like, let me just show it here for you. When you have this future return that you collect, if you open it up in this form, and if you just factor out this discount factor here, right? The blue term that you see here is, again, the future return, right? But for time t plus 1, correct? So you could say that your current future return is your immediate reward plus the next future return, right? Clear? So what is the future return that I'm going to do? If I do know what future return that I collect in the next time, right? I only need to know what is my next reward, right? And then I up to that future return, it's going to be my future return in time, right? So if I do know what is happening in future, then I can just recursively go back in time, right? Now, if we write it down, if we do a tiny bit of messy calculations like the other one we did today, then we're going to end up with the Bellman equation, which is going to give you this property. The value of any cell is depending on the value of everybody else for any policy. And now, this cell depends on everybody with some equation. This cell depends on everybody with some equation, and so on towards the end. You have n cells, n equations, right? So you check the value of the n cells. You put them inside those n equations. You solve the system of equations. you end up with the value of all the cells, right? This is what we call it Bellman equation. Okay? So eventually, you don't need to do what I did today. So good news, please come over on Tuesday. You don't need to do that one, but I hope that messy calculation motivated you why this Bellman equation is important. One